Welcome to the course on Power Electronics with wide bandgap devices. Today I am going to discuss about application of wide bandgap devices in integrated motor drives or IMD, as you can see in this particular slide. Okay, so what is IMD or integrated motor drive? So basically, integrated motor drive, as you can understand from this title, it is basically combining motor and the drives together. So basically integration of electric motor with a motor drive which improves power density and reduces system cost. So it is expected to the reduce the system volume or improve the power density, that is in the range of, so volume of the system will reduce volume will reduce 10 to 20%, right? And it will reduce the cost of the system by 30 to 40%. So majorly the reason why people are focusing in this particular application is because it will reduce both size and the cost. So this is like the kind of range which is expected to be achieved by using wide bandgap devices in place of silicon devices. Okay. So now this wide bandgap devices, it can be anything, silicon carbide or GaN, operate at higher temperature and offers efficiency benefit. As the system size reduces, obviously the power density will improve. And the thing is that when the wide bandgap devices will be use with uh, by considering the application such as integrated motor drive, so then what will happen, it will be able to operate at much higher temperature. So basically motor applications, it is very important to choose a system which should be able to sustain at high temperature, because the temperature which will be generated from the motor, it will be much higher than the power electronics converter. So if the converter is mounted on the motor itself, then the system needs to be operated at that temperature. So that is why we need WBG devices which is suitable to operate at high temperature, and obviously the efficiency is something which we are looking forward to. So that is also possible to achieve by using wide bandgap devices. So these integrated motor drives are widely used mainly in aerospace, robotics, automobiles and off-road vehicles. Okay, these are the different things which is used. So as you can see, these are the main advantages of using wide bandgap devices. Along with it, the another important advantage will be there. So that is, so basically it improves electromagnetic interference or EMI and electromagnetic compatibility or EMC due to direct connection of the drives to the motor, right? So this is one of the main advantages, like most of the wide bandgap devices, as I have discussed earlier, so the problem of EMI is severe, and in order to reduce this EMI we need to measure this EMI whether it is within the range or not. If it is not, then we need to design the filter. But this direct connection anyway will help to reduce this EMI, so then it will be possible to reduce the use of filter in this particular application. Okay, so the thing is that the modularization of wide bandgap devices can significantly and hence performance of integrated motor drive in fault tolerance, efficiency, power density, and high temperature operation. So these are the advantages of use of electric motor along with the drives together by using these wide bandgap devices. Means it is possible to use motor and drives together by considering silicon devices as well, but it will not have advantages of wide bandgap devices. One of the main problem is that silicon based converters, the size of the converter is much higher than that of the wide bandgap devices. So mounting of that particular converter on motor will be very difficult. So that is the first disadvantage of silicon based converter, and it will come in the middle for using that converter for IMD applications. The second thing is that this converter, like silicon converter, it is not suitable to operate at high temperature. Means the temperature limit of silicon devices is much lower than that of the silicon carbide or GaN devices. It is expected to use these wide bandgap devices till 300 or 600 degrees Celsius, right? But whereas in silicon devices it is mentioned 200 degrees Celsius. It is mentioned in the data sheet. It is not suitable for any application. Means the device can sustain till that temperature. That means whenever the converter will be operating, so the converter overall temperature we need to control it much below that level. Right? As I have discussed the temperature related issues in the devices. So the silicon device, if we mount on the motor itself, the temperature which will be generated in the motor and the converter both will be so much that it will exceed the limit of the silicon device's temperature, maximum temperature. So that is why it is important to use a device which should be capable of operating at much higher temperature. Right now, wide bandgap devices, they are suitable to operate at much higher temperature. It is expected that they will be suitable to operate for this kind of drives. Right. Now, you can see here this electro-hydrostatic actuators overview. So basically, it is the full form is electro-hydrostatic actuator. So it is known as EHA. Right? EHA actually systems eliminate servo valves offering better efficiency, reliability than the conventional system. They have high force capabilities with low parasitic losses, but can be limited by increased volume and weight from the added components. And the EHA utilizes an electric motor driven bidirectional magnetic pump in which the inefficient servo valve is eliminated. Okay. Another advantage is that the overall efficiency of EHA higher than higher due to low parasitic losses, while the hydraulic transmission system still provides, which is already mentioned in the first point, provides high reliability. With extremely high force capability. Okay. Now, how to configure this integrated motor drive? So there are like various configurations. So in the reference, these configurations are also given along with the diagram. So basically there are actually basically four types. You can see here. So radially housing mounted, which is also known as RHM, which is based for high speed motors with longer stacks than diameters. Then the second one is, the first one is this one. Second one is axially housing mounted. So it is suited for high torque motors with larger diameters than stack lengths. Third one is radially stator iron mounted. And the fourth one is axially stator iron mounted. This is suitable for compact designs for tighter integration, but they require better cooling medium. Right. So these are the four different types of configurations which are used for integrated motor drives. Since drives will be connected to the motor, the positioning of the drives, how it is going to be in the motor, so that defines these four different categories. So the pictures you can get from the references. So obviously it is related to the construction of the machine. So different types comes. So any of this can be used in any type of the motor. So that depends on the application and the advantage of that particular type. Then it will be considered as integrated motor drives. So now, why we need to consider wide bandgap devices? It is the basic principle of the wide bandgap devices again will be used. So low switching losses, high power density, high temperature operation, right? These are the benefits, but obviously there is also disadvantage uh, of this wide bandgap devices used in the integrated motor drives. That is, the cost is still much higher than that of the silicon devices. Although the cost is much higher in like WBG devices, any of the devices as compared to silicon, but the saving in other areas like cooling and the passive components, that overall result will be reduction of 30 to 40% of the cost, even though the device cost is much higher. So that is why people are focusing into the application where it is very important, or probably it is like it will solve many other purpose. Okay, so now when we say wide bandgap devices we are going to use, so we cannot directly use, as I have discussed earlier, the challenges of using wide bandgap devices. If we have to use wide bandgap devices, again the technological development should be such that one thing is that cost need to reduce down, but at this moment that is not possible, that is not a problem. But the converter configuration, how it is going to be. Conventional silicon devices, when it is used for any application, so the converter configuration, it can be such that which will be suitable for application of silicon devices. But now, as we are going to consider wide bandgap devices, it has different requirements in terms of drives, in terms of application, or maybe, as I have already mentioned in the previous slide, so it is actually suitable for fault tolerant application. Now, if we are going to consider fault tolerant application, so then obviously the converter configuration should be such that it will be able to handle the fault which is happening in the motor. Then, how the converter configuration should be. So, one of the important thing I have discussed, like this wide bandgap devices application should be such that we can use advanced converter configuration. How this is going to be? So if we say this is fault tolerant and modularization, IMDs are modular, provide better integration, curved surface and fault tolerant operation. But we have to see what kind of converter will be suitable, or we need converter which will be novel for this wide bandgap device applications. Different inverter topologies such as 4 leg, 6 leg offer varying level of fault tolerance, right? So we have to focus on the converter which will be fault tolerant converter. So it is one of the converters. So you can see here in figure A, it is 6 leg inverter with single DC link. So the DC link which is at this particular point, and the inverter it is having 6 leg. So 6 leg, each leg, so basically combinations of 2 leg, it is connected to one of the phases. So if this is phase A, let's say, and this is phase B and this is phase C. So what is happening? 2 legs are connected to phase A, 2 legs are connected to phase B, another 2 legs are connected to phase C, and it is having obviously some inductance and the resistance in between. Okay, so this is 6 leg inverter with a single DC link. So this is used for fault tolerant 3 phase inverter for integrated motor drive applications. Now this is another one is the, this is 4 leg configuration. There are like different type of configurations which are used for fault tolerant operation. The previous one was 6 leg, now this is 4 leg. You can see here. So here also single DC link is there, and then 3 legs each are connected to 3 different phases, right? A, B, C, and the common point is connected to 2 legs. So this is how this converter is used for fault tolerant application. So there are other converters also. You can see here. This is cascaded inverter with separate DC link. Instead of using 2 different legs, we can have 2 different converters. Means in 6 legs. So 6 leg inverter. Here also 6 legs are there, and in this case also 6 legs are there. But here what is the difference? The DC link are separated. So it is divided in 2 DC link rather than 1 DC link. So here it is DC link and DC link 2. Okay. So now it is like conventional voltage source inverter. So this is the 3 leg. So it is connected to A, B, C. Similarly, this is also connected to A, B, C of the other DC link. Okay. Now there are other converters also, 3 single phase inverters. Instead of connecting single DC link, separate DC link can be connected to separate phase. So like in 6 legs, so there are like 2 legs connected to the phase. So here also the same thing is there. So the configuration remains same. Only thing is that DC link now is divided for each phases. So DC link 1, DC link 2, DC link 3. So you can see here there are like these converter configurations. They are not very different from the conventional converter configuration, but the way these phases are connected, that will help the converter to protect during faulty operations. So fault tolerant kind of converter, right? So this kind of converter can be used for this integrated motor drive applications. So now these converters, anything if it is in use, so the important point is that the requirement of the cooling, what it is going to be, because you know for motor drive application cooling has to be proper in order to reduce the heat whatever will be generated in the converter itself or due to the motor, the device, whatever heat will be generated in that system. So that we need to take care of. So there are actually various industries. They have used this wide bandgap devices for IMD applications, and they have different kind of cooling medium. So one of the important cooling is that. So I can just write down here. So basically, the important technologies, the key enabling technologies for the IMDs are the advanced cooling system. So this tells us advanced converter configurations. So along with advanced converter configuration, we need advanced cooling system as well, right? This cooling create water screen between motor and the drives. Okay. So this cooling system, like conventional cooling system, will not be suitable for IMD application. We need special kind of cooling, and for that, exploration in the cooling area is very important for any of the application of wide bandgap devices. What are the different cooling are in use by the industry, right? So Siemens. So you all are familiar with the Siemens technologies. So Siemens, what they did, so they are actually invented one cooling. Cooling operates water screen as water screen between motor and drives. Okay. Now another industry which is known as NPTEL. What they are using? So basically NPTEL develops it is silicon carbide based motor drives suitable for high frequency high sun temperature with significantly reduced volume and weight. Okay, so like different industry, they are using different uh, methods in order to use the system for IMD applications. Okay, now this Yakawa, they are developing, what they are using, it is actually developed a compact and pinless 3 kilowatt gallium nitride based motor drive which generates much lower losses compared to so you can see here the Siemens, Nidec and Yakawa. So Siemens basically they have developed the cooling medium. Then Nidec they have developed the silicon carbide based motor drive, and then Yakawa developed gallium nitride based motor drive. So like depending upon the kind of devices, so like this drive can be taken from that particular industry, and then again like the it will be connected to the motor. So the cooling medium can be selected from the suitable places. So here Siemens cooling can be operated in between the motor and the drives. So like that is how the system can be jointly connected together, right? So these are the advanced converters as I have discussed. So now what are the devices which are suitable for this application? So you can see here, so there are like different industries, they have different devices like Cree, Infineon, Mitsubishi, ST Micro, Genesis, Microsemi, USCI, Rome, Semicron. So these are the different manufacturers. So the voltage level here we are focusing at like higher level. So you can see here the voltage level, it is from 900 to 1700 from Cree. It is Infineon 1200, and then Semicron it is like 1700. So the current level, as you can see here, so current level minimum it is 5 ampere and maximum it can go till 300 ampere. So that it should be suitable for megawatt level power level application. So the junction temperature you can see here. So the junction temperature for silicon carbide devices, it is expected to be able to handle till 150 degrees Celsius. The device itself is suitable to operate at much higher temperature, but when it is connected to the system, so it should be able to handle this much temperature. And the structure type is also given, the packaging is also given, the thermal management, whether like what kind of thermal management is required. Here heat sink is mentioned for all the devices, and then it is like the different like it is leading provider, SBD, modularization, different type of the devices are mentioned here, and all these devices are suitable for IMD application. So similar to silicon carbide devices, the gallium nitride device is also suitable for this drives applications. So you can see here, so the gallium nitride devices, obviously the power level will be much smaller than that of the silicon carbide device. Silicon carbide device is suitable in megawatt level, whereas the gallium nitride device, it is suitable to much lower power level in kilowatts level. So you can see the voltage level, it is like 15 to 300 volts from EPC, transform it is 600 to 1200. Again, like GAN system, it is 100 to 650. TI, it is 48 to 600. So these are the different voltage levels that are available. Now current is also given. So maximum current is given here 90 amperes. So substrate, what kind of substrate are in use? So like they have different substrate for different companies. Some is using silicon, some silicon carbide, some gallium nitride, sapphire. And the maximum temperature here also is mentioned as 150 degrees Celsius. One of the important thing is that, so when the device is operating at high temperature, the properties of silicon carbide is much better than that of the silicon or the GaN devices. GaN device is having much lower junction capacitances, which will allow it to operate at much higher frequency. But when it goes for the high power level, then the silicon carbide device is suitable than that of the GaN device. Okay. So now the operation of silicon carbide device at higher temperature is also much better. So the packaging type is also given. Here the thermal management for GaN devices either heat sink or through the PCB, right? And also like the different packaging type is also given: low voltage, no packaging, conventional packaging, integrated gate driver. So these different packaging are given. So you can explore all these devices. You can see what will be suitable for IMD applications. Accordingly, you can choose. So the challenges is that, so whenever these wide bandgap devices are in use for any integrated motor drive application, the issues include synchronization of multiple controller and the need for sophisticated kind of cooling system. As I said, cooling, some of the cooling like is currently available, so that can be used. But like advanced kind of cooling system, what will be more suitable? So that kind of work is still going on. Now, the permanent magnet switch reluctance motor machines offer opportunities for improved performance. So, like the applications of integrated motor drives in this kind of motor, how it is going to be, so that kind of exploration need to be done. Okay. So, these are the references for this particular discussion. Okay, thank you. That's all for today.